Swayam Prabha. Digital India. Educated India.
Well, just a quick revision. So what we have done through the means of two different protocols, two different algorithms, is established the following theorem. So recall what we have shown is that a proportional allocation. So an allocation which is fair in the sense that everyone receives an interval, a connected piece of value at least 1 over n times the value for the entire resource, always exists. And furthermore, this can be computed efficiently even in this general Robertson Web query model. In this query model, where the sort of agents know their own values, and what you get to do is just query them, ask them, okay, how much do you value this interval? If you start here, where would you sort of cut to achieve a particular target value? So within these two eval and cut queries, we can sort of, with a polynomial number of queries, we can find proportional allocations that achieve proportionality. So valuation queries in the Robertson web model, which is again the very natural query model of interacting with agents through these two types of queries, and very specifically, like the moving knife procedure achieves this using n square queries. N again is the number of agents in my fair division exercise, and the second one we saw was this recursive algorithm by Even and Patch, and this required, in fact, 2n log n queries. So sort of something, the number of queries that's sort of proportional to the sorting thing. Okay, fine. As I said, what good is a theorem if you don't know 3 or more proofs of it? We have 2. There are others, something called like a last diminisher. There is in fact a randomized algorithm as well by Edmund and Pruse. But the natural question now is that, okay, can we do better? Like, we kind of, with this nice recursive idea, we have gone down from n square queries, a quadratic number of queries, to notably a smaller query count, which is of n log n. So like good engineers, like good computer scientists, natural question is, okay, can we do even better? As in, can we say find a proportional allocation, say in linear number of queries? And the answer is actually no. And this is no, again, provably so. So the way this is done is by establishing a lower bound. And I'll just give a proof sketch of this lower bound, but I'll mention the result in its entirety. This is by Edmund and Pruse, and again the handbook of computational social choice, the reference that I had pointed out earlier, is a good place to sort of read the details of this result. And the theorem of Edmund and Pruse says that if I look at any proportional So by a proportional procedure, I mean a protocol, an algorithm that finds a proportional fair division, finds a division where everyone receives an interval of value at least 1 over n. Then in the sort of Robertson web query model, in the query model that we've been looking at, then any such proportional protocol procedure algorithm needs omega n. Right, so effectively what this means is that the up to constants the even paths, the recursive method we saw is in fact provably optimal. You cannot develop a protocol, provably so, which outperforms this procedure in terms of the number of queries you need to find a proportional allocation. This is a very nice, tight matching lower bound. It's a day of celebration when you actually find a result where there's an algorithm and a matching lower bound. So certainly a rarity. It's sort of a tiger sighting of sorts. So something to sort of appreciate. Very quickly, the way this is done is so I hope everyone is sort of familiar with this omega notation, right? This just means so standard big O notation. Roughly speaking, this means that if you give me any algorithm asymptotically, if it finds a proportional fair division, then it will have to query, like either cut queries or eval queries, and the total number of queries will be at least n log n, right, up to constants, which are sort of that hidden in this omega notation. Okay, so the proof is somewhat technical, though not very difficult, but the key, let me actually mention the key idea or sort of the key construct that goes into it. And the fact is that, again, this is a proof sketch. I'm not going to sort of go over through the entirety of it. But the key idea is that if you are finding a proportional so if you are finding an allocation, say I1 through In, where again the agent I receives interval II, then for a large number of agents, you would have actually found such an interval of small length, right? So note that if I give you one specific agent and ask you, okay, give me an interval. So I give you an agent A. I'm not concerned about other agents. And for this agent, I ask you, give me an interval such that this interval is of value at least 1 over n for this agent A. How can you blindly answer, give me back a response? So let me ask the question again. I fix an agent, one special agent. For this agent, I want an interval such that this interval is of value at least 1 over n for this fixed chosen agent A. My question to you is, how can you answer this question without much effort? What was that? Just return the whole cake, right? Trivial. You just, I mean, I fixed any. There's no concern for any other agent, right? If this is sort of a super entitled agent and you really don't want to worry about other agents, there's a very simple way to find an interval that satisfies this inequality. Just set IA to be the whole cake. The value is 1, you get it, fine. But note that what's sort of difficult in proportionality is you want to achieve it simultaneously, you want to achieve it for all agents. What this does impose upon you is the fact that for a large number of agents, the length of the interval that they obtain in, say, this proportional allocation will not be too large, right? So what I'm saying is that let's do this. Let's look at the length of an interval. So what is the length? It's just literally the length of I in particular. So say IA is x, it's an interval from x to y, the length of IA is y minus x. It's just the physical, it's this length of the interval. Now note that if I sum this up across all agents, what do I get? So I have my allocation. So this is I1 through In, again in some order. So agent 7 receives this, agent 4 receives this, so on and so forth. IA is somewhere. So these are the intervals assigned, disjoint intervals. So if I sum the lengths of these intervals, what do I get? 1, right? It's just literally just summing up these lengths. So this is 1. So this effectively through an averaging argument that I'll detail in a second means that for so what I'm saying is that if I look at an allocation, in fact, it doesn't even have to be a proportional allocation. Just the fact that it is a partition of the cake means that for a large chunk of agents, for at least half of the agents, if I look at the length of the interval that they have received, that length cannot be more than 2 over n. Right, and the proof of this observation is simply by contradiction. Say this is not the case. There are more than n by 2 agents who receive an interval of length more than 2 by n, the sort of, I assume the opposite towards a contradiction, then so towards a contradiction, if n by 2 agents have sort of the length more than 2 by n, well, if you sum their intervals up, then that length, the sum of lengths would be just summing up these n by 2 agents would actually come up to be more than 1. There are n by 2 of them, each guy has 2 by n, multiply these two numbers out, what you get is something strictly more than 1. This cannot happen. Again, I'm writing down formally a sort of very obvious fact, which is that on average, I mean, a large number of people cannot be more than much higher than the average. Note that the average length here is actually 1 over n. The n people, their total is 1. So the average length is 1 over n. And this is sort of just an observation that follows out of it. If you want to sound fancy, this is what's called Markov's inequality. Right? So interpreted in a probabilistic context, this is nothing but that. But again, it's sort of a simple averaging thing that, like, if I look at the average height of individuals in this room, it cannot be that half of you are of height more than twice the average. Here's the proof. Very useful fact in many contexts. So fine. So let me kind of keep this out. So what it boils down to is that when you find a proportional allocation, you are not only ensuring that all the agents get a large value, you also ensure that you also, in the process, you also achieve the fact that the length of a bunch of these intervals is small for right. So again, I'm just erasing down the definition of length. I kind of hope this is the standard enough to keep in mind. So what this says is that, look, like it's not just finding high values. The another task at hand is to actually find this high values in fairly small length intervals. So that actually complicates things a bit. So again, individually, if I fix an agent and I ask you for an interval that achieves value 1 over n, it's a very simple task. Once I've fixed the agent, you can just tell me, okay, look at the whole cake. Obviously, that's one interval that achieves a value of 1 over n. At the same time, if I just focus at this property in isolation, so I give you an agent and I ask you, okay, give me a interval IA that is of length less than 2 by n, what can you do? So if I just wanted to find an interval with just the second property, how would I go about doing it? Well, I'll just pick any interval of length less than 2 over n, just the first one, from 0 to 2 over n. So, I mean, length is completely independent of value, you're good to go. So, in isolation, these two properties are easy to obtain. What's important to note here is that when you have a proportional allocation, you are achieving both of these two properties simultaneously, which is what kind of makes things difficult. You have to now know the valuation well enough such that you achieve this sort of proportional value of 1 over n in a small enough length. And this is what sort of makes the problem difficult. So, the term used in the proof of Edmond and Proust is that these are what are called rich intervals. Intervals that achieve a value of 1 over n. Intervals of length less than 2 over n are called thin intervals. That's the jargon they use. And the sort of key observation, again, not being too formal, is that so one has to find like rich and so in order to find a proportional allocation for a large number of agents, or at least half the agents, you will have to find an interval that's both rich, i.e. has a large value, and at the same time thin, right? And the point is that, so this implies that if I define Tn to be the time required to find such a rich and thin interval, the time to find a proportional allocation is sort of lower bounded, is at least n times Tn. So this omega is sort of hiding this factor of 1/2, but that's sort of the formal implication. Again, I'm being sort of not going over all the details, but one can argue this formally, that if Tn is the time required to find it for one specific agent, given the fact that the valuations of players are distinct, like knowing one agent's valuation tells you nothing about any other agent's valuation, means that if you have this Tn, you will need to spend this much amount of time to find a proportional allocation. This Tn gets multiplied by a factor of n. What this lets you do is sort of isolate the problem. Now you can look at one specific agent, because this problem of finding a rich thin interval is a agent specific problem. It's not a problem that requires all of the agents together. So with this Tn, what's shown, and something that I'm kind of omitting right now, is that this Tn itself is omega log n. You cannot achieve this for a very sort of structured family of valuation using less than log n queries. This is sort of a nice construction. It's a valuation that's sort of based on a particular tree that's imposed on the cake. So something that's sort of worth reading. But yeah, in the interest of keeping things simple, I'll not kind of go over it. But the point is that you kind of reduce the proportional to this problem of finding rich thin intervals, and actually you get a major advantage of n here. So this by itself gives you a omega n lower bound, which is not that interesting. But what you can show is that this, for any specific agent, when you have n agents, this is sort of finding thin rich is at least log n, right? So note that, like, though this is dependent on a single agent, the fact is that the thinness and the richness has a factor of n, and hence that kind of shows up as a log n here. Again, if there's interest in the sort of the tutorial section or one of these offline sessions, we can kind of go over it. What's notable about it is it's a standalone lower bound. It does not rely upon lower bounds on other problems. It sort of does not piggyback on other results. So it's a sort of fairly nice self-contained result. And for a specific agent. So it's a, yeah, so you fix an agent A and you say that an interval is rich for that. Thinness is again universal. So the problem, so fix an agent A, the problem of finding a thin rich agent is find an interval which is of this sort. I mean, note that, in some sense the idea is you have to do sort of a binary search over like roughly n by 2 intervals, and this is sort of where log n sort of comes in. I mean, that doesn't really translate into a formal proof. To obtain a formal proof, you have to construct valuation classes, but in the lower bound actually piggybacks on this problem, which is sort of nice in and of itself. So here's a good question, the answer to which I'm not, sort of open question to me, is that say I actually give you an algorithm that for agents finds thin rich intervals. So let's just, again, this is a exercise whose answer even I'm not completely sure of. So you have an algorithm that's given to you as a subroutine. You can feed an agent to this subroutine along with some interval, and the algorithm will return a thin rich interval, like a sub-interval of what you have given as the interval that you have passed it on, if one exists or says there isn't one. Now, using that as a subroutine, can you find a proportional allocation in exactly, like using order n invocations to that algorithm? So that would be a nice converse connection, which I'm not sure is a sort of nice open question worth thinking about. Okay, so that kind of is the proof sketch I wanted to address regarding proportional divisions. This in particular, as I mentioned earlier, shows that the recursive algorithm that we have seen is in fact optimal. You cannot hope to design a method, a protocol that finds a proportional allocation within n log n number of, like, within order n log n number of queries. So with that, we are at the end of proportional cake divisions. Yeah, so if there's any solace, and if you think this was messy, what I can tell you is that Envy-Ffeenes is even worse. Their like negative results abound, and indeed, like we have seen that Envy-Ffeenes implies proportionality, so in that sense it's likely a harder solution concept. It turns out it's a fairly elusive solution concept. It's this sort of the level of generality that we have enjoyed with proportional allocations does not sort of continue to carry on when working with envy-free solutions. Okay, so that's the length and breadth of what I wanted to talk about proportional allocations, fair division with respect to proportionality. I'll now move on to envy-freeness. Okay, so again, so I'll say that an allocation is envy-free if, again, obviously no one is envious, so every agent looks at the interval that's assigned to it, and this is of value at least IB for all agents in participating in the fair division exercise. So this is just a repeat of the definition. No one wants to swap, no one values someone else's interval more than their own. So now though, let's kind of relax it a bit and sort of consider like each IA to be sort of so we actually got a very nice property with proportional fair divisions, that is everyone got a connected piece. No one, like the cake, that part of the cake that you received wasn't like crumbed up and wasn't chopped, cut into finely, chopped into fine pieces. I mean, for like going ahead a bit, this sort of nice result is not possible in the case of envy-freeness. I'll formally state what this means soon. So towards that end, let's relax it and consider a setup where I actually allow you to assign each agent a bunch of intervals, but a finite union of them. So what do I mean? I mean that, let's say I have the cake 0, 1. So now agent A can get this piece, this interval, and a third interval here. So again, the intervals that I assign to different agents are pairwise disjoint. I cannot like pick a piece and say, okay, it's going to both two players. But what I can now do is that look at a case where the single agent actually receives a union of intervals. So it's a finite union of intervals. So the scenario looks like this. Again, the subscript denotes the agent's index, the agent that receives these three. The superscript, say, denotes the sort of the index of the piece. So what could happen is that IB gets here, and then agent B also receives these two pieces. So this is how it is. So so in the case of proportionality, how many cuts did I make to find a fair division? So there are n agents. How many cuts did I need? What is that? 2 agents, how many cuts did I make? N minus 1, perfect, right. So n minus 1 gives you n pieces and you just shuffle them around. And now I'm saying, okay, fine, I'll make more than n minus 1, I'll kind of partition it and like shuffle. So you like this part and this part, you get these two, I like something in the middle, I'll get that, so on. So it's certainly a relaxation in the sense that I'm allowing more flexibility to you, fine. And the question is, okay, now can you do something interesting? Now can you find envy-free allocations? So let me start with the bad news first. And this is major bad news, right? It's like the Sensex falling of sorts. And the idea here is, so the first sort of the first negative result, which again is somewhat technical and will require some sort of constructs to be cleared, something called rigid measure systems, can be done, but yeah, it's sort of will be a bit intricate for the purposes of these lectures. So I'll just state the result, explain it, and happily move on for both of us. The first negative result is by Stromquist that actually shows that so the first one says, like, look, if you stick to allocations, if you stick to the requirement that every agent must get a single finite time, bounded time, yeah. So the first negative, strong negative result by Stromquist says that, look, if you want to stick to the requirement that every agent must get a connected piece, you're out of luck. Forget poly time, forget exponential time, forget n to the n to the n time. There isn't a finite time algorithm that will find it for you, right? It's a strong negative result, but it's in a model where it's in again the Robertson web query model, but it's sort of an adaptive adversary, which means that there's an adversary sitting behind who's answering these cut eval queries, the Robertson web queries that you ask, and he's kind of adversarial. He'll shift based on whatever you have asked so far. So it is in a strong model, a strong adversarial model, but still it's a drastically negative result. And like, to sort of rub salt in the wound, this actually holds for n equal to 3. So why can't, or can I expect this can I expect to strengthen this result for n equal to 2? Can I work hard and achieve such a negative result for 2 agents? No. Why? The cut and choose protocol does it for me. For 2 agents, like the first thing we saw was Envy-Ffeenes for 2 agents. So I already have a finite, forget finite, it's a 2 query. It's a 1 query thing. You just ask the first guy cut, ask the second guy the eval. So 2 or 3 queries, you're done. So for 2 agents, you essentially need 3 queries. For 3 agents, you need the unbounded number of queries. So in terms of jumps, it's a big one. It's a strong negative sweeping result, right? So, okay, sort of, I was kind of foreshadowing this for quite some time. The next question is fine, now that you have given us a relaxation where I can look at crumbs, assign agents a union, finite union of intervals, well, then what can you do? So it's not necessarily a negative result. Okay, it depends on what you call negative. I actually I like the result, so I'll not quantify it as negative. But for the second case of There's this nice result by Aziz and McKenzie. It's not too old. It's in fact a result from 2016 that gives a finite time algorithm. But in terms of, it's very generous with the word finite. So it finds, so again, in this sort of non-contiguous model, because for the contiguous model we have this negative result, and both of these are in the Robertson web query model. So it finds an envy-free division using, okay, let's start n to the 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 n queries. Right, so it's a tower of n's, and I challenge you to give me another algorithm with this matching running time bound. Furthermore, I challenge you to explain this algorithm to me. Right, so it's certainly non-trivial. If you feel tired now, we can have an entire summer school dedicated to these results. It's a tower of 6 n's. Yeah, so this is a rarity, but yeah, it's up there. So that's the number of queries you'll need to find an envy-free allocation. Fine. You can say, okay, maybe the problem is genuinely difficult when you allow for, even when you allow for this relaxation. But here is where the community working on cake cutting needs to shy away and hang its head a bit. The lower bound for this is n square. Right, so again, lower bound not in this contiguous pieces setting, it's in the finite union, it's omega n square. However, which way you look at it, there is a large gap between these two. Right, try plugging in 3 and computing this tower of n. Probably by the end of this week you'll find that number. It's a large gap. It's like a starking, like it's a sort of blatant open problem facing us. But yeah, this is sort of, it's a challenging open problem as well. It's not obvious how to sort of bridge this gap. And again, this is sort of intuitive, but the idea is that like not too many connections are known between like lower bounds of these things versus lower bounds for other like more well-studied problems. So going back to the lower bound for proportionality, going back to the result of Edmond and Proust, the n log n one, well, there it was standalone. So it's actually nicer in some sense, again, from a sort of understanding perspective, if you connect problems, connect to things that you already know are hard. So that's in some sense lacking. This is what kind of a very rough, intuitive, high-level idea why there's a large gap between the lower bound and this upper bound. So it's a Envy-Ffeenes, again, the purpose of this slide is to convince you of the fact that if you want to find, if you go in a party with even 3 people, and you really want to find an envy-free cake cut, yeah, good luck. Yeah, this is, the party will end before this thing so runs to completion. What is that? It's again through like constructing families of valuations. It's similar. There's some work by Nissan and some, like it's again these sort of extension of these rigid measure systems and so on. So the lower bounds are sort of it's again constructing particular valuations and saying that you have to query it enough times before something meaningful can be extracted. Yeah.